Good evening, everyone. Great to be here. I'm Simon. I'm an iOS developer by day, but by night, or by the last year at night, I've been building a HTTP server with Swift Concurrency called FlyingFox. And I kind of started building it because I think Swift Concurrency has probably been the one feature that's captured my imagination the most over the last 10 years, probably since Swift itself has come out. I remember reading Chris Lattner's manifesto on Swift Concurrency from 2016 or 2017, and then just tracking all of the changes until it was released. And like any good engineer, how do you learn something is you just build something that you're not very good at, and you refine it, you improve it, and eventually you start to learn and understand it. So this talk, it's not really getting into really technical details, but trying to bring together some musings of in my journey of building this. So we'll go through what FlyingFox actually is itself, from the Swift package that you can get on GitHub. We'll look at a little bit of its structured concurrency, how it uses it, some of the async sequences that it uses, and then we'll touch a little bit on some non-blocking I/O and things of how you can actually get some network, you can get some network communication using structured concurrency, and we'll look at FlyingSocks, which is a submodule, and then to round it out, some tips when you're asynchronously testing things, because that can be a nightmare. So FlyingFox is a HTTP server. It's on Swift. It's written in Swift. You can run it on Swift 5.5 plus. It's lightweight. So the goal I really had was you want this to compile. You want it to be zero dependency, compile really fast, be simple to use. And the use case, I have comes from being an iOS developer. So being able to integrate this with an app, or to use it alongside an app to help support the test process is really the direction that I was coming from. So even though it's focusing on supporting apps, it supports Linux and Windows as well, just because that was more my curiosity on how you get all of that to work. I'm sure nobody actually runs it on Windows at all, but you can. Linux actually, it was really easy to get Linux to work, and I actually run it on a few servers in Docker, which is using Linux. It only supports HTTP 1.1 and WebSockets, which is good enough for my needs at the moment. So inside the package, you'll see there's the FlyingFox part, which is really the high-level HTTP protocol components that you kind of use. And there's another module that you can also use called FlyingSocks, and that's really just a socket communication, and it creates the bridge for your to the async world. Because all the sockets that we use have been around for 30, 40 years, and it's just adding that bridge. I'm actually using it where I'm working at the moment to support the development process. I run a few low stakes HTTP or websites and services on it myself. I actually run it in Docker on Google Cloud Run behind their reverse proxy. So that's my recommendation of how to run it. But if you're really serious about Swift on the server, I would point you to SwiftNIO. If you want high performance, you want it to be secure, standards compliant, extensible, if you want HTTP 2, look at SwiftNIO. FlyingFox doesn't do any of that. Promise to do any of that. So yeah. But what SwiftNIO will do, it'll take forever to compile. If you're on Intel, you'll be looking at least a minute, 2 minutes If you pull in OpenSSL, there'll be even more. It's complex. You can do so much. So there's a bit of a learning curve as well. So if you're not wanting to pull all that in to your project, you might want something a bit simpler. It's also Swift System, which Apple put out. So this was a good reference for me. So this is really just a Swift wrapper on top of these low-level calls, which is multi-platform as well. But that doesn't support any async await calls. But that was a good reference for me. So the story for FlyingFox, it really starts, kind of here in the middle. So this is the typical way HTTP servers work. You have a request coming in, and the server gives a response. And I was using servers to do some testing and support my process, and this was working exactly like that. And then I wanted to bring in async, because we all want to do that. And then I think everyone here is probably familiar. As you do that, these effects are viral. It spreads throughout the code base. The calling function needs it. And they're the really obvious effects. But it also spreads lower as well if you do things correctly. So we'll look at how it spreads upwards and how it spreads downwards in the code base as well. So this was really just all I wanted to do. And next thing you know, I've built an entire server just to do this. So of course there's easier ways. You can take your function, you can wrap it in a task. So this is one way. You could do it this unstructured way, straight away you can look at that and say, look, what happens with cancellation? What happens if you want to stop those requests? If you've just fired the task off and it's running, yes, it'll work, but you can't cancel it. So in FlyingFox, we use structured concurrency. So at the moment, we use a task group. You can see that we're waiting for connections to come in. Those connections are modeled via an async sequence. And then we start a new task for every connection to handle that. And that works really well. These are slightly wasteful. I think Amy mentioned SE381, I can see it on my slide, which is discarding task groups. So that's coming in Swift 5.9. And the waste there is that every child task that you start with a server like this, you don't really care about the response. You just want it to end, and then you want everything to be discarded. So there's a few bytes that actually get leaked at the moment just with the throwing task group. Even though there's no result, there's a few bytes just in the pointer to the task and its structure itself. So Swift 5.9, I'm really looking forward to that. But as the concurrency spreads upwards through the code base, if you handle it properly with FlyingFox, you basically get this as your interface to start the server. So if your main.swift just imports FlyingFox, you can start the server just like this, and it will run. And it will run forever until it runs out of memory, because we're not using a discarding task group. But yeah, and this makes use of top-level concurrency. So execution will be suspended inside server.start until an error is thrown. You can interrupt the process, but that's all you really need to do if you're using Docker to run FlyingFox as well. Is that there's a heap of support in FlyingFox for handling requests and doing things, which I'm not really going to touch on this evening, but you can kind of see that with a request you could return any response. And with those things in place, you end up with this nice structured task tree. So the server starts, and it starts 2 child tasks. There's a pool, which we'll talk about a little bit later. There's a listen task, and that's the task that's going to be listening really for your connections that are incoming. So that's constantly running. And when the connection comes in, that connection gets its own task. So it can handle the connection. And another connection comes in, it can handle 2 connections. And each connection then processes requests one at a time, but they just run inside their own task. When the connection finishes, it goes away. And finally, the whole server goes away. So the top level inside FlyingFox kind of relies on a few async sequences. So the listening task that runs, waiting for connections. There's an async sequence that really just gives you a connection. So you can have that pattern where you do for, await, a connection, and every connection that comes in is sent in the sequence. So you can see there, it just pulls through there. The other sequence that we've built is basically like a byte sequence. And the sequence that I'm using is not buffered beyond what's buffered in the socket. So for a HTTP request, you basically need to process the header byte by byte, and once you get through the header, you can then process the body in larger chunks. And it's amazing that once you've got a single sequence of bytes like this, you can easily transform that into something a little bit more useful. So a sequence of bytes, you can use that to map that into a sequence of requests. And once you've got those components built, it almost starts to write itself. The code to actually run the server and parse the requests, you obviously have to write the HTTP protocol parts, but once you've got those key Swift concurrency parts, the actual management of the server takes kind of care of itself. The hard part is getting some of those pieces. So an async sequence or a, I can't remember what else we mentioned. And the hard part is because half of these, or all of these calls by default, they block. If you're not, and we want it to be non-blocking. If you're not sure what non-blocking is, it's probably easier to think about what actually is blocking. So I think everyone is probably familiar with this old API that's been around for a very long time that basically loads data from a URL. And if you load that from a network synchronously in your app, basically, you typically see the user interface lock up, nothing happens, and then it continues. And that's just because the API blocks while it executes it. So non-blocking API is API that doesn't block. So you're probably all familiar with just the completion handlers, which are non-blocking. They're so familiar to us, we use them all the time. And the newer APIs that suspend, so they don't use completion handlers, but they suspend, so they're non-blocking. So you actively want to avoid blocking, and especially in Swift concurrency. We see the user interface lock up, and that looks bad, but blocking in Swift concurrency is almost just as bad for concurrency. So you can try naively to not block. You might think, I'll wrap this in a task like this. And yes, this might get something off the main thread, but it's still going to block. And it's going to block one of the threads in the cooperative thread pool. You can try even harder. And you think, oh, maybe I'll do a continuation. I'll basically do the same pattern, but it still blocks a thread in the cooperative thread pool. And the cooperative thread pool, Apple, it doesn't really have much documentation on it. There's some references. This is a good session in DubDub from a few years ago, Swift concurrency behind the scenes, that goes to explain some of the details. but I think they deliberately hold back some of the details and don't want to make promises in the language beyond what they've said here. But basically, the cooperative thread pool works by keeping the number of threads limited. So Apple, they promise that the number of threads used in your application in the default cooperative thread pool will match the number of cores that you have. So if you have a phone with 4 cores, there'll only be 4 threads processing your async events. And the benefit there is that there's a limited number of cores, or there's a limited number of threads running, but they're quickly switching processing coroutines, so the tasks getting processed want to be moving through them quite quickly. So there's less thread context switching and more coroutine switching. And because that means that actual threads are quite limited, they're quite valuable. So if you do make one of those blocking calls, you're actually blocking one of those really precious threads. And if you block them all, everything that you're running async in your app will actually grind to a complete halt. So the number one thing, I suppose, to remember is never block if you, in an async method or a task. And if you have to block, then try and do that on a dispatch queue. So the last resort, if you don't actually know that there's better APIs to use and you really want to use this data with contents of, at the last resort, then jump out to a dispatch queue. And that will at least block a dispatch queue, but will keep one of the threads, will keep all the threads in the cooperative thread pool available to process things. So with that in mind, FlyingSocks is the module that provides that async interface. So there's really kind of 3 types in there. We've got this socket type, and that socket is it's my cross-platform overlay or wrapper that sits on top of the system calls that live underneath. So Linux and macOS system calls for sockets, very, very similar. They're basically functions that take unsafe mutable pointers. They take values. They return result codes. So my layer that sits on top of that manages all that specifically for each platform and Windows. And then any errors that it gets, it actually throws. So it gives you that nice affordance to, instead of checking error result codes and checking random global error number variables, it'll just throw. An async socket basically takes a socket and exposes it asynchronously. And to do that, it needs something to help with its blocking, and that's the async socket pool that I use. So when you look in the code, an async socket really just takes a socket and it takes the async socket pool, and that's basically your interface. And the first thing you do, because by default sockets and file descriptors, they all block by default. So the first thing you do is set an option. So this is the high-level API that FlyingSocks gives you, but this maps to a low-level system call. And you can set that socket to go into non-blocking mode. What that means is that now when you try to read data from it, it's not going to block like we saw before. It'll actually return straight away, and it returns with an error. So my overlay, when it's actually going to block, instead of blocking, it throws an error to say it's blocked, which is great. We don't actually block, but we don't know when data is going to be there. So we could loop and go, let's try again. Let's sleep for a few seconds. Maybe the data will show up, and that can all work. But it would be really nice to know when data is going to be ready. But that is actually quite a hard problem. So what FlyingSocks does is it takes the pool and it uses the pool to suspend until something's ready. So the socket here, we try and read from the socket. There's no data there. It throws an error, we catch the blocked error, and we tell the pool, now suspend us until there is something to read. When there is something ready to read, the pool resumes the task, it reads from the socket again, and it continues. And it all kind of seems simple. And the problem is those APIs that you need to use to notify you that something's ready on a socket, they're all different on every platform. There is one high-level API, like the Windows version that's the poll version. There is a version that you can run on every platform, and that kind of runs in user space, and it's not as efficient, and it's not as it's actually a little bit more difficult to use. But macOS, there's KQ, and you basically can ask the kernel to tell you for a certain socket when is there any events available, and the same pattern is on epoll on Linux. And it is just a little bit cumbersome because the semantics of those APIs aren't 100% aligned. So it's not just simply mapping names; it's also doing like some slightly different processing there as well. And then all these system calls all block as well. So while we've done our best to kick this blocking concept, or avoid blocking as much as possible, we've almost now got to the end of the line, and we've got these blocking calls we have to make just to be notified. So what FlyingFox does is it uses a dispatch queue to do that final call to block, that final blocking call to notify that there's data available for on the sockets. And instead of every connection having its own dispatch queue and basically having its own thread, it is using a shared queue. So every socket kind of shares the same pool, just to use that to share it that way. And if you might remember from earlier, we had the task diagram when the service starts. So that's the pool that runs at the very top. So every connection that comes in uses that pool to manage its own sockets. And if that pool throws an error, those tasks end, and then finally the server will end, so the start function will throw an error, and you'll see something printed in your console. And then testing this stuff. So building FlyingFox and building its tests and testing its functionality was very challenging. I think everyone's probably had experience with asynchronous testing. If you haven't used async away, you maybe have done some UI testing, and they're notoriously flaky and they're difficult to write. It doesn't matter how much experience you have, I think everyone can struggle and have problems with them, and it's just because there's so many combinations and possible states the system can be in, and it's really tricky to get across all of it. So there's some tips that I've kind of learned that we can kind of go through. So adding logging I found super important if you've got tests and it's not, it might be working fine when you manually just test it, but when you're trying to automate some testing and getting it to be reliable, it's failing sometimes. So adding logging is really, really helpful. So you can see that flow. There's so many layers in the system that's asynchronous. Working out exactly what the what was happening, so trying to observe all of those layers. So if there's logging in your system, it can help. And this was a big one. So avoiding overlapping tests. So by that, that means you can run tests in parallel, but sometimes your test finishes and there's code still running. And when there's code still running, it could be doing something and the next test starts. So it can be handy to wait for the first test to almost completely stop. And if you want it to wait to completely stop, sometimes you've got to make sure that all the cleanup has happened. So if you've started the HTTP server and you cancel it, you might need to wait until the cancellation is finished and there is an error before you start the next one and you continue. And I had this really, really hairy bug where it was failing sometimes, some tests were failing sometimes in some scenarios, and it ended up being like, a bug in the app where this FlyingFox server was actually closing a socket twice. So you close a socket, and then when it was unwinding and all of those tasks are closing, it was closing the same socket again. And it was, ignoring the error because the socket, couldn't be closed. It didn't really exist. But if you know about sockets and file descriptors, they're really just numbers. And sometimes if you're super unlucky and the tests overlap, the next server has started and its file descriptor, its socket is the same number, and then the server that's shutting down is actually closing the socket for the next server. So it looks like this server just started, but it just died straight away. And yeah, just ensuring that the tests actually completely finish and tear down can help there. And test cancellation. So cancellation, a lot of the time I've found like a lot of people don't think about it too much, but if you're writing if you're writing continuations yourself, and if you're actually writing cancellation handlers, then I'd recommend testing it, because it's probably one of the toughest aspects, I think, the cancellation handler in Swift concurrency to actually use correctly. So I'd write tests that your tasks that you start, you can actually cancel. So in your tests, avoid blocking API as well. So even waiting for expectations like this, I think in recent versions of Xcode, it actually tells you now don't do this. But this was a real pitfall, very early on. And even other blocking API, you might think, oh, this is not in my app. I will. It's okay just to block here. It's fine. But even starving resources when you're running your tests can cause issues. Because a lot of the time, flaky tests run differently on different hardware, and if you use these blocking APIs, it actually starves resources for your test itself, and it can make that more flaky. I think early on that I had written a test that was using expectations like this in an async method, and I think running it on a GitHub Actions node, which possibly only had 2 CPU cores, so that may have meant that there's only, that would have meant there's only 2 threads in the cooperative thread pool. And just waiting for an expectation would mean my task was just never completing at all. And it was like really weird. You're like, why is that task just never completing? And then removing expectations, basically removing that blocking call, fix the issue. Now, I think Apple now, they recommend use this API if you're using expectations. I actually found I don't actually need to use expectations in the asynchronous tests that I write. Repeatedly run tests. So if you didn't know, you can select a test in Xcode, and you can run it thousands and thousands of times. If you're lucky, your tests will fail, like your test that's flaky will fail early, and it will fail repeatedly, so you'll be able to fix it. If you're really unlucky, you might have to run it up to 10,000 times, which I've found sometimes actually reproduce it. So the way you get this is, I think when you're looking at your tests in Xcode, it's normally like that little diamond that you can click and it turns green when everything's all good. So if you right click on there, you can say run this test repeatedly, and you can edit it and say run it 10,000 times. And the other aspect I've really observed is like different behavior on different architectures, and that's I suppose that's expected when your tests are asynchronous, and they're there's issues. They're different depending on different circumstances of each machine. They're going to have different a different sequence of events and a different aspect. So So sometimes I've found that a test was only failing on Intel, and it's probably nothing to do with the architecture. Probably just because that machine runs it in a certain way. If you're running things on GitHub Actions, at the moment they're all Intel nodes. There's no Apple Silicon on GitHub Actions yet, and if you're using Apple Silicon, then it can be infuriating. So if you do have like another machine lying around, or if you've got access to some virtualization, you can try and run your tests in virtualization as well and see if it's easier to make them break. Oh, good. And that's pretty much the end. So thanks for listening about my journey through trying to build this FlyingFox server. And please take any questions if people have any questions or
yeah. Thanks, Simon. Any questions?
Have you done performance testing with it?
Oh no, I should have mentioned in there that I deliberately haven't tried to performance test. So the performance tests I've done are basically serving Xcode on my machine through curl. So the testing I've done has like been a few connections. Or, what kind of throughput do I get through it? Not how many connections can I handle at once. And I tell myself that when I run it on Google Cloud Run, that its load balancer will just spin up more Docker containers for me when I need to.
I'm more interested about the XC-test performance features, right? Where you can automate the testing of performance, but I guess you haven't done that.
Yeah, no.
I was going to ask something similar in terms of how you determined the dispatch queue was the best method to sort of stop blocking. Like, did you have any sort of test around what would happen or the implications of not using dispatch queue?
Yeah, so if you, so I've run some tests that if you just spawn a task, say a task group, and then you add in, 10, 20,000 tasks, that's fine. Swift Concurrency will handle that. But if you put a blocking call in there and you see how slow everything will go through, you can either, you can immediately grind it to a halt. It's actually quite noticeable. So I think, and some of the tests that I have done, like you can start off and you can see there might only be a couple of threads running, and then if you try and spawn 10, 20,000 tasks, within a few seconds, there'll be, the tasks will all be running, matching the cores on the machine. And if you did the same test with dispatch queues, more and more dispatch queues and more threads, and you'll have thousands of threads. And that's one of the issues with dispatch queues is the thread explosion that can occur. But if you're executing thousands of blocking tasks, then dispatch queues solution is to just spawn another thread so work will get done.
Any other questions?
Love the talk. Remind me a lot of uni days. So a bit of a tangential question. Have you had to deal with any endianness differences, like big endian, little endian, or anything like that? Or are you working at a bit higher of a level?
So when you run on Apple Silicon and ARM, the endianness is the same, and I think in the HTTP protocol everything's expected in the same endianness. I can't remember if it's big or little, but I use the one that the HTTP protocol standard uses.
Which is the correct answer.
Anyone else?
And yes, on uni days, I had did socket programming like 23 years ago, and it was so much fun building this. Like, it took me right back to when I learnt this, running it on the Yulara terminal with RMIT, all down this way. Yeah, it was great.
Good old BSD sockets.
Yeah.
Thank you, Simon.